Welcome back to the Deep Dive. Today, we have a really fascinating, and I've got to say, a pretty dense stack of material in front of us.
It's definitely not light reading.
No, not at all. Usually, we're kind of floating up in the clouds here. We're talking high-level software, API design, maybe some nice, clean Python scripts.
We live in the penthouse, basically.
We live in the penthouse of the computing world, exactly. The views are great, it's climate-controlled, and everything is, nicely abstracted away.
You don't have to think about the plumbing or the wiring. It just works.
Right. But today,
Mhm.
today we're sending the elevator back up. We're grabbing a flashlight, putting on a hard hat, and we are going down to the basement.
Lower than the basement, I'd say. We're going straight to the foundation.
We're in the crawl space,
Yeah.
and there are definitely exposed wires down here.
Oh, yeah. Watch your head.
We are looking at a chapter on ARM architecture
Mhm.
and specifically bare metal programming. And the hero of our story today is the ARM Cortex-A8 processor.
Mhm.
Now, I want to pause on that for a second because the notes really highlight this specific chip. It's an older chip, isn't it?
Yeah.
Why are we focusing on the A8?
It is, yeah. But in the sort of the genealogy of modern computing, the Cortex-A8 is a pivotal moment. It's like finding a key common ancestor.
How so?
Well, it was the first ARM processor to implement the ARM v7 architecture. And that might sound like just, alphabet soup, but what it really meant was this was the point where ARM chips stopped being just for, like, your Game Boy or the controller in your microwave.
Right. Simple, dedicated devices.
Exactly. The A8 was the inflection point where they became powerful enough to run a full modern operating system. We're talking Linux, we're talking Android.
But this is the key part, while still being efficient enough to run on a battery, right?
That is the magic trick. Precisely. Before the A8, you kind of had to choose. Do you want raw power, in which case you're using a hot, power-hungry Intel chip that needs a fan?
Right, something you plug into the wall.
Or do you want battery life? The A8 was the moment where the industry realized, wait, we can actually have both. If you've ever used a BeagleBone Black, you've used this chip, an early iPhone, an early Android phone, you had this architecture in your pocket. It's where mobile computing became, for lack of a better word, real computing.
And that term bare metal that we're
Yeah.
using. I mean, my first thought is a heavy metal band made up of robots.
Which I would absolutely go see, just for the record.
Oh, me too. 100%.
Yeah,
But for our purposes today, it means programming with absolutely no safety net, doesn't it?
that's it. No Windows, no Linux kernel, no Mac OS to manage your memory or catch you when you fall. It is just your code and the raw silicon.
So you're not asking the operating system to, please draw a window on
No,
the screen.
you're not asking. You are commanding. You are manually calculating which memory addresses correspond to which pixels and flipping the bits yourself. It is the absolute source code of reality for that device.
It sounds tedious and dangerous.
It's both. But it's also absolutely essential if you want to understand how our devices actually think.
So the idea here is, if we can understand the Cortex-A8 at this fundamental level, how it moves data, how it makes decisions, we basically have the blueprint for almost every mobile device that came after it.
Exactly right. The supercomputer in your pocket today is really just a Cortex-A8 on, massive, mass amounts of architectural steroids. The fundamental DNA is still there. If you get this, you stop being just a user of technology and you start to become a mechanic. You can look under the hood.
I love that. Okay,
Wow.
let's pop the hood then. The very first concept that the source material just hammers on is this acronym, RISC. RISC. Reduced Instruction Set Computing. It sounds like a minimalist lifestyle for computer chips.
Does this instruction spark joy? It's honestly not a bad analogy.
So what's the alternative?
The alternative is CISC. CISC, Complex Instruction Set Computing. And that was the reigning philosophy of the desktop world think Intel for decades.
Okay, so give me the mental model. RISC versus CISC.
All right, imagine you're building a house. In a CISC world, the Intel world, you have this incredible all-in-one power tool. You pull the trigger, and it drills a hole, inserts a screw, sands the wood, and maybe even paints it. It's one very complex, very powerful command.
So in my code, I just say build wall, and this one instruction triggers a whole chain of events inside the chip.
Exactly. You might have a single assembly instruction that says something like, go to this specific spot in memory, grab a number, add 5 to it, and then store it back in the same spot. One command. But designing the hardware for that super tool is a nightmare.
I bet. It must take millions of transistors just to decode what that one command is even supposed to do.
It does. And all those transistors generate heat and consume a ton of power.
So ARM comes along and says, what?
ARM, with the RASC philosophy, says, let's throw away the super tool. Instead, we're going to give you a very simple screwdriver, a very simple hammer, and a very simple saw.
So if I want to build that same wall, now I have to issue 3 separate simple commands. Fetch the screw, turn the screw, put away the screwdriver.
That's it, exactly. You, the programmer, have to write a little more code. The instruction set is reduced to its bare essentials. But here's the magic. Because each tool is so simple, the chip can execute each command incredibly fast. And crucially, the hardware is so much simpler that it stays cool and sips battery. It's why your phone doesn't need a cooling fan.
Okay, that makes perfect sense. Simpler tools, faster execution, less power. But this leads directly to what was, for me, the biggest aha moment in the notes, but also the biggest hurdle to get my head around. It's this idea of a load store architecture.
Ah, yes. This is the first great filter for anyone learning assembly.
Right, because in Python, or even C, if I want to add 2 numbers, A and B, I just write A plus B. I don't care where A and B are physically located. The language handles it.
The language is doing an enormous amount of work for you behind the scenes. In the ARM world, at the bare metal level, the CPU is extremely picky. It literally cannot do math on data while it's still in memory.
Wait, say that again? It cannot do math on memory?
It cannot. The core part of the CPU that does the math, it's called the arithmetic logic unit, or ALU. It has no direct wires connecting it to the main memory, the RAM, for doing operations.
So if I have a variable stored at memory address, say 1000, I can't just tell the CPU, add 5 to whatever's at address 1000.
Nope. The CPU is blind to it. It has to be brought in first. This is where we need a good analogy. Think of the CPU as a master chef in a kitchen.
Okay, CPU is the chef.
And the main memory, the RAM, is the giant grocery store down the street.
All right, I'm with you.
The chef cannot chop a carrot while that carrot is still sitting on the shelf in aisle 3 of the grocery store.
That would be absurd, yeah.
It's impossible. So there is a strict 3-step protocol you must follow. Step 1, you must load the carrot. You have to send a delivery truck, that's the memory bus, to the store, find the carrot, and bring it back to your kitchen counter.
And the kitchen counter. In this analogy, these are the registers.
Bingo. The registers. They are a handful of tiny, incredibly fast storage locations right inside the CPU core itself. On the Cortex-A8, you have R0 through R12 that are your general kitchen counters. So the first instruction is LDR, load register. Load the value from memory address 1000 into register R0.
Okay, so the carrot is on the counter. Now I can chop it.
Now you can run your ADD instruction. ADD R0, R0, hashtag 5, add 5 to the value in R0, and store the result back in R0. The math happens on the counter, but here's the part that trips people up.
What's that?
The value in the grocery store is still the old one. It hasn't been updated.
Right, of course. You only changed your local copy on the counter. The store's inventory is unchanged.
Exactly. So you must perform step 3, store. You take your newly modified value from R0 and you send the delivery truck back to the grocery store to put it back on the shelf. The instruction is STR, store register.
Load, process, store. LDR, ADD, STR. It feels like a lot of extra work. Why this separation?
It feels like work for the programmer, but for the hardware, it's a dream. It means the memory access part of the chip and the math part of the chip can work independently. The chef doesn't have to wait for the delivery truck to get back before starting to chop. It lets you build that pipeline, that assembly line that we'll talk about later. It's all about keeping the hardware busy and efficient.
Okay, so we're in the kitchen. We have these counters, the registers. The notes give us a tour. R0 through R12 are the general purpose ones.
Yeah.
Those are just our scratch pads, right? For whatever we're working on.
Correct. Your variables, your loop counters, temporary results, they all live there. But then you have what I call the special trio, R13, R14, and R15.
They sound important.
They control the entire flow of the program. If you mess with these 3 without knowing exactly what you're doing, your program doesn't just crash, it sort of ceases to exist in a coherent way.
Okay, let's break them down. R13 is the stack pointer, or SP.
Right, the stack. Imagine you're in the middle of preparing a dish. You've got your chopped carrots and onions on the counter, and suddenly a rush order comes in for a different dish. You can't just throw your current ingredients on the floor.
You have to set them aside. Save your current work.
Exactly. You put them all on a plate, and you put that plate on a tall stack of other saved plates. That stack of plates is the stack, which is a special area in memory. And R13, the stack pointer, is the finger that is always pointing to the top plate on that stack. It tells the CPU, this is the current safe spot to save things.
So if R13 is pointing to the wrong place, you might put your plate down on top of someone else's dish.
Or you might put it down where there's no table at all. That's a stack overflow. The whole thing comes crashing down.
Okay, so R13 tells us where to put our stuff.
Yeah.
Next is R14, the link register, or LR. The notes call this the crumb trail. I like that.
It's the Hansel and Gretel register. It solves a fundamental problem. When your code calls a function, say, you jump from your main program to a little subprogram that calculates sales tax, the CPU teleports to a new location in the code.
But eventually that sales tax function finishes, and the CPU has to know how to get back to where it came from.
Precisely. It needs to know the way home. Before the jump happens, the hardware automatically saves the return address into R14, the link register. It leaves a crumb. When the function is done, it just says, okay, where's the crumb? Ah, there it is, and it jumps back to the address stored in R14.
But wait, what if that function calls another function? Doesn't the new return address overwrite the old one in R14?
Ah, you've spotted the trap. Yes, it absolutely does. If main calls func.a, the return address to main is stored in R14. If func.a then calls func.a, the return address to func.a overwrites what was in R14.
So now you can get back to func.a, but you can't get back to main. You're lost.
You're lost forever, unless, right at the beginning of Funky,
The first thing you do is save the value of R14 onto the stack. You put your return address on that stack of plates for safekeeping before you make another call.
And then when you're done, you pop it back off the stack.
That is the fundamental dance of all low-level programming. Push the link register, call, pop the link register, return. If you forget, your program goes off into the weeds.
That's fascinating. Okay. And the last of the trio, R15, the program counter, or PC.
This is the big one. The program counter is not just a register, it's the embodiment of execution. It holds the memory address of the instruction that is currently being executed. As the program runs, the PC just ticks forward like a metronome. Address 1000, then 1004, then 1008. It's the heartbeat of the CPU.
So if I'm a hacker, or if I just want to implement a jump or an if statement, I can just manually write a new address into R15.
Yes, writing a value to the program counter is the raw, unfiltered GOTO. You are literally teleporting the flow of execution to a new place. It's incredibly powerful. But if you write a bad address,
You teleport into a wall. You teleport into the middle of your data or into empty memory, and the CPU tries to interpret random numbers as instructions, and everything just stops.
wow, so R13 manages the data, R14 manages the history, and R15 manages the present.
A perfect summary, and sort of watching over all of them is one more special register, the CPSR, or current program status register.
The dashboard.
The dashboard, exactly. It doesn't hold data, it holds flags. Was the last math operation negative? Was the result 0? Did it cause an overflow? Are we in a privileged mode? It's the context for everything else that's happening.
So much going on. Now let's shift gears a bit. The notes bring up something that feels like a kind of split personality for the chip. It apparently speaks two different languages, or dialects. We have ARM mode, which is A32, and then Thumb 2 mode, or T32. Why would a chip need two dialects?
Yeah, this is a really clever bit of engineering that goes back to that core RISC trade-off between power and efficiency. Standard ARM instructions, the A32 set, are rigid. Every single instruction add, load, store, anything is exactly 32 bits or 4 bytes long.
So it's predictable. The hardware knows it just has to grab a 4-byte chunk every single time.
Exactly. It's like speaking in full, perfectly formed, grammatically correct sentences. I would like to add these two numbers now, please. It's very clear, very powerful, but it's also verbose. It takes up a lot of space.
And on a small embedded device, memory is a precious resource.
It's everything. So ARM's engineers came up with an alternative called Thumb. Originally, Thumb instructions were all 16 bits, or 2 bytes long. It's like switching from formal English to texting shorthand. Add 2 nums PLE.
You can fit a lot more text messages on a page than you can formal letters.
Right, you get much better code density. You can pack almost twice as many instructions into the same amount of memory. But like texting, the original Thumb was limited.
You lose some of the nuance.
You lose a lot of it. You couldn't access all the registers. You couldn't do certain complex operations. So what they created for the Cortex-A8 was Thumb 2, which is a hybrid. It's a variable length instruction set.
So it uses 16-bit instructions for the simple, common stuff, and then expands to 32-bit instructions when it needs to do something more complex.
You've got it. It's the best of both worlds. The publisher is smart enough to figure out if it's looking at a short instruction or a long one.
But the notes say this isn't just about saving storage space. It can actually make the code run faster. How does smaller code run faster?
This is a really critical point. It's all about the cache. The CPU cache is a tiny little block of super fast, super expensive memory that sits right next to the processor core. We're talking maybe 32 or 64 kilobytes. It's prime real estate.
Okay, so space in the cache is at an absolute premium.
The highest premium. Now, if your code is more dense, if it's written in Thumb 2, you can physically fit more of your program into that tiny cache at once.
Which means the CPU doesn't have to go on that slow trip to the grocery store, the main RAM, as often to fetch the next instructions.
Bingo. Every single time, the CPU needs an instruction that isn't in the cache. It's called a cache miss. It has to stall. It sits there and waits. By packing the code tighter with Thumb 2, you reduce cache misses. And less waiting means a faster program, even though the instructions themselves aren't inherently faster.
And the processor can just switch between these two modes whenever it wants.
Yep. There's a special instruction, BX, which stands for branch and exchange. It basically says, jump to this new address, and by the way, when you get there, start interpreting the code as Thumb, or vice versa. The decoder inside the chip literally reconfigures itself on the fly.
That's wild. It's like telling your brain to switch from reading English to reading French mid-sentence.
It's a pretty amazing hardware trick.
Okay, so we've got the kitchen, we've got the languages. Now we need to talk about the security guards. The notes call them modes, and it says the CPU has trust issues.
It has to, right? Imagine if every app on your phone had complete unrestricted access to the hardware.
It would be chaos.
Total chaos. Your favorite game could accidentally reconfigure the clock speed and overheat the chip. Or a buggy calculator app could just wipe the operating system.
So we need a system of privilege.
A very strict hierarchy. At the very bottom, you have user mode, or USR. This is the padded cell where all your applications live. From here, you can't touch any of the critical system control registers. You can't disable interrupts. You can't change the memory map. You are sandboxed.
But sometimes an app needs to do something real, like write a file to disk or send a packet over Wi-Fi. It needs to get out of the padded room.
It does, and to do that, it has to politely ask the boss for help. And the boss operates in one of the privilege modes.
The notes list a few. What's the main one?
The main one is supervisor mode, or SVC. This is typically where the OS kernel lives. When your app wants to do something privileged, it executes a special SVC instruction. This acts like a doorbell. It triggers an exception, the CPU switches into supervisor mode, and the kernel takes over, examines the request, and decides if it's safe to perform.
So the app never touches the hardware directly. It submits a request to the kernel.
It's a trust broker. Then you have other special modes for emergencies. You have IRQ for general interrupt requests, like a key was pressed on the keyboard, and FIQ for fast interrupt requests.
FIQ sounds like it's for more important things.
It's for the real hair-on-fire emergencies, something that is extremely time-sensitive, like a data buffer that's about to overflow. And it has a secret weapon to make it so fast.
Ah, this is the banked registers thing. I saw that in the notes. It sounded like a magic trick. R8 through R12 are banked. What does that mean?
It is one of the most clever latency hacks in processor design. Let's go back to our kitchen analogy. Normally, when an interrupt happens, when the boss runs in with an emergency, you have to stop what you're doing and clear your workspace.
You have to save all your current variables from R0 to R12 onto the stack.
Right, you have to push your context. That takes time. Pushing a dozen registers to memory might take dozens of clock cycles. In a high-speed system controlling, say, an anti-lock braking system, dozens of cycles is an eternity.
You could crash the car in that amount of time.
You could. So for FIQ, the hardware does something amazing. When the FIQ exception occurs, it doesn't force you to save R8 through R12. Instead, it just swaps them out.
Swaps them out.
Imagine there's a hidden panel in your kitchen counter. When the FIQ alarm goes off, that panel instantly rotates, revealing a completely separate, fresh set of R8 through R12 registers that were hidden away.
Oh, so you don't have to save the old ones because they're not even there anymore. You just get a clean workspace instantly.
Instantly. No saving, no restoring on the way out. You just start working on the fresh registers immediately. This makes the entry and exit time for an FIQ handler incredibly, incredibly fast. It's designed for things that cannot wait.
That is seriously cool.
Okay.
Let's go even deeper into the machine. Let's talk about the pipeline. The Cortex-A8, the notes say, has a 13-stage pipeline. Why so many stages?
Speed. It all comes back to speed. It's that car factory assembly line analogy again. If you have one person build an entire car from start to finish before starting the next one, you'll produce maybe one car a day.
Because most of your tools are just sitting idle most of the time.
Exactly. But if you break the process down into 13 stages, Stage 1 gets the chassis, Stage 2 attaches the wheels, Stage 3 installs the engine. Then you can be working on 13 different cars at the same time.
So at any given nanosecond, the Cortex-A8 has 13 different instructions in various states of completion, all moving through it simultaneously.
Yes, and it gets even crazier. The A8 is dual issue, which means it actually has 2 parallel assembly lines. If the instructions are independent of each other, it can start 2 new cars at the exact same time.
That's just mind-bending.
Yeah.
But there's a huge catch, right? The assembly line works great as long as the line is straight. But code has branches. It has if statements.
Yes. The great enemy of the pipeline. The branch. Your code says, if x is equal to 5, then do this, otherwise do that. The problem is, the result of is x equal to 5 might not be known until stage 8 of the pipeline.
But the front of the pipeline, stage 1, needs to fetch the next instruction right now to keep the line moving. It can't just stop and wait for 8 cycles.
If it waited, the entire factory would grind to a halt. The whole benefit of the pipeline would be lost. So the CPU does something that sounds insane. It gambles. It predicts the future.
It guesses.
It has a very sophisticated branch predictor unit that looks at the history of that if statement and says, you know, the last 100 times we were here, x was not equal to 5. I'm betting it's not equal this time either. And it starts speculatively fetching and executing the instructions down the otherwise path.
It starts building the car for the otherwise path before it even knows for sure.
A perfect way to put it. And if its prediction is correct, it's a huge win. There's 0 delay, 0 stall. The pipeline stays full, and performance is amazing.
But if it's wrong?
If it's wrong, it's a disaster. It has to trigger a pipeline flush. All 13 stages of speculative work are just vaporized, thrown in the trash. The front of the pipeline has to be reset to the correct path and start all over again.
And you've just wasted a ton of time and presumably a ton of energy doing work that gets deleted.
You are literally burning battery power to compute nothing. This is why writing predictable code with fewer surprising branches is so critical for performance in low-level systems.
And the notes mention ARM has another trick to avoid this. Conditional execution. The ADDQ instruction. Add if equal.
This is a classic ARM superpower. On many other architectures, if you have a short if statement, you have no choice but to branch. If condition is true, jump over the next instruction.
Which puts the branch predictor at risk of guessing wrong.
Right. With ARM, you can just tag almost any instruction with a condition. You can say ADEQ, which means, Mr. CPU, only execute this ADD instruction if the 0 flag is currently set. Otherwise, just ignore it.
So the instruction still flows through the pipeline.
It does. It takes up a slot on the assembly line. But when it gets to the execution stage, the hardware just checks the condition flags. If the condition is false, it just turns the instruction into NOP, no operation. It does nothing.
But the crucial thing is, the pipeline never stopped. It never flushed.
Exactly. The flow remains smooth. It's an incredibly elegant way to avoid costly short branches.
Okay, so that's the brain. Let's go back to memory, but this time with a gatekeeper. The Memory Management Unit, or MMU. The source calls this a translation layer.
The MMU is the guardian of the system's sanity. It sits between the CPU and the physical memory. When your app asks for, say, memory address 0 by 1000, it's not actually getting the physical memory chip's address 0 by 1000.
It's asking for a virtual address. It's being lied to.
It's a very useful, benevolent lie. The MMU takes that virtual address, looks it up in a set of translation tables set up by the kernel, and says, the application's virtual address 0 by 1000 actually maps to physical RAM address 0 by 8C4F000.
Why do this? Why add this extra step of translation?
2 huge reasons. Isolation and flexibility. The isolation part means every single application can believe it has the entire 4 GB address space all to itself. Your web browser and your music app can both use address 0 by 1000, and the MMU makes sure they map to different physical locations so they don't corrupt each other.
It's what stops one crashing app from bringing down the entire phone.
That's the main job. But for us, in bare metal land, the MMU has another critical role, setting attributes for memory regions. This is where you can shoot yourself in the foot.
The notes mention normal memory versus device memory, and the trap of caching.
A deadly trap. Normal memory is your standard RAM. The MMU can mark this as cacheable. This tells the CPU, hey, feel free to cache reads and writes to this area for speed. You can reorder them if you want. It's all good.
Which is great for performance when you're just doing math.
Right. But then you have device memory. This isn't RAM. This is a hardware peripheral that's mapped into the memory space. A status register for UART, for example. If you accidentally tell the MMU that this hardware register is normal cacheable memory, disaster strikes. Let's say you want to read a status register to see if a character has been received. If that read gets cached, the CPU will read it from the hardware once, get the value false, and then store that false in its cache. Every subsequent time you read that register, the CPU will just give you the fast cached value of false without ever checking the real hardware again.
So you could be hammering keys on the keyboard and the software's just stuck in a loop, reading false, false, false from its cache, completely blind to reality.
And that is a nightmare to debug. The code looks perfect, but it doesn't work. Then you add a print for debugging, which slows things down and changes the timing, maybe causing a cache flush, and suddenly it works. You remove the print, and it breaks again.
Terrifying. So the rule is, any memory-mapped hardware must be marked as non-cacheable and strongly ordered.
Absolutely. Which leads us to the next topic, barriers. The notes say ARM has a weakly ordered memory architecture. That sounds bad. It sounds bad to a programmer, but it sounds fast to a hardware designer. Weakly ordered just means the CPU gives itself permission to reorder memory operations for efficiency as long as it doesn't break the logic for a single thread.
So if my code says write to address A, then write to address B, the hardware might actually perform the write to B first, if the bus is available.
It might. And if A and B are just independent variables, who cares? The result is the same.
Yeah.
But if address A is a register that says, here's the data, and address B is a register that says, go process the data now.
Then the order is critically important. You could be telling it to process garbage.
Immensely important. And this is why we need memory barriers. They are explicit instructions that act like fences. A DMB, or data memory barrier, says, hey, CPU, make sure all memory accesses before this barrier are visible before you execute any memory accesses after this barrier. It enforces ordering.
It's a traffic cop. Nobody crosses this intersection until the previous traffic is cleared.
A perfect analogy. And there are others, like DSB for synchronization, which actually waits for writes to complete, and ISB, which flushes the entire instruction pipeline. Use that after you've changed a fundamental system setting to make sure no old instructions are still lurking in the pipe.
Okay, we've laid all this incredible groundwork. How do we actually talk to the outside world? Peripherals and GPIO.
We do it through memory mapped I/O, or MMIO. We've touched on this, but the core idea is that hardware devices pretend to be locations in memory.
So address 0 by 4800 at 00 might not be RAM, it might be the control register for a system timer.
Exactly. And to turn the timer on, you just write a specific value to that memory address. But this is where high-level languages like C can fight you. The notes bring up a crucial keyword, volatile.
Ah, volatile. I see this sprinkled in embedded C code. It basically tells the compiler, don't get clever with this variable.
That's a great way to put it. A modern compiler is an aggressive optimizer. If it sees code that says, write 1 to address X, and then later, write 1 to address X again, it might think, that's redundant, I'll just delete the second write.
Which is fine if X is a variable, but if it's a hardware register that needs to be pulsed.
It breaks your hardware. Or if you're in a loop waiting for a status register to change, the compiler might say, this value never changes inside the loop, so I'll just read it once before the loop starts and check that cached value forever. Volatile tells the compiler, trust me, this memory location can be changed by forces beyond your knowledge. You must perform every single read and every single write exactly as I wrote it.
It's the disable optimization flag for a single variable.
Precisely.
Now let's get even more basic. GPIO. General purpose input output. The pins on the chip. The notes mention pin muxing, which makes it sound like the pins are confused about their identity.
They are multi-talented. A modern chip has hundreds of internal functions, USB controllers, UARTs, SPI ports, timers, but it only has a limited number of physical pins coming out of the package.
You can't have a dedicated pin for every single function.
No, it would be the size of a frisbee. So most pins are shared. A single physical pin, say pin 23, could be configured to act as a simple on-off GPIO pin, or you could reconfigure it to be the transmit line for UART number 2, or the clock line for an I2C bus.
And you, the programmer, have to make that choice.
You have to write to the pin multiplexer, or MUX, registers first, to tell that pin what its job is for today. If you forget to do this, you can write to the GPIO control register all you want, but the pin is internally connected to the UART, so your signal hits a dead end, another silent failure.
And on top of that, there's pad control.
Yeah, that's setting the electrical characteristics. Do you need an internal pull-up or pull-down resistor? What's the drive strength? How much current can the pin source or sink? It's where the digital world of software meets the messy analog world of physics.
Okay, there's one more really important hazard in this section. The read-modify-write hazard. This sounds like a classic concurrency bug.
It is the poster child for race conditions in embedded systems.
Walk me through it.
Okay. Imagine a single 32-bit register where each bit controls a different LED on a control panel. You want to turn on LED number 5, but leave all the others untouched.
So the natural way to do that is, step 1, read the current 32-bit value of the register. Step 2, modify that value in my CPU register to set bit 5 to a 1.
Yes.
Step 3, write the new 32-bit value back.
Exactly. Read, modify, write. Now what if, right between your read and your write, an interrupt occurs? The CPU pauses your code to go handle something urgent, like a button press.
Okay.
That interrupt service routine needs to turn on LED number 10, so it does its own full read, modify, write cycle on that same register. It reads the value, sets bit 10, writes it back, then it finishes. LED 10 is now on.
And now control returns to my original code, which was paused.
It returns to you. But what value are you holding in your CPU register? You're holding the value from before the interrupt happened, the value where bit 10 was off.
Oh, no.
You then proceed with your step 2, setting bit 5, and then your step 3, writing that stale value back to the hardware. You just successfully turned on bit 5, but you also accidentally turned bit 10 back off.
I overwrote the interrupt's work without even knowing it.
You clobbered it. This is why good hardware designers provide a solution. Atomic set and clear registers. These are separate addresses. If you write a value with a 1 in the 5th bit position to the set data register, the hardware will atomically turn on just that 1 bit, leaving all other 31 bits completely untouched.
So you don't need to read first. You just issue a single atomic write command.
It removes the race condition entirely. It's beautiful.
Speaking of being interrupted, let's talk about the mechanism itself. Section 7, interrupts. When the hardware needs to get the CPU's attention.
It's the hardware tapping the CPU on the shoulder, or for an FIQ screaming in its ear.
And the mechanism relies on something called a vector table.
The vector table is the emergency contact list for the CPU. It's a predefined list of addresses at a fixed location in memory, usually right at address 0. When an exception or interrupt happens, the CPU automatically stops what it's doing and looks up the correct address in this table to find out where it should go.
So it's like if a reset occurs, jump to the address at index 0. If an undefined instruction occurs, jump to index 1. If an IRQ occurs, jump to index 6.
Exactly that. It's a hardwired dispatch mechanism, and the code that handles these events has to follow a very strict ritualistic sequence.
Right, the notes lay it out. Mask interrupts, switch mode, save context.
You have to. When an interrupt hits, the hardware automatically does a few things. It snatches to the appropriate mode, like IRQ mode, and it disables further interrupts so you can't be interrupted while you're already handling an interruption. It also saves the return address to R14RQ and the old status register to something called the SPS IRQ.
And then it's up to you, the programmer, to save any other registers you plan to use.
Correct. You push them to the stack, you handle the event, you pop them back from the stack, and then you return. But the return is weird. The notes point out this strange detail about the return address offset. Ah, yes. The infamous ARM pipeline offset problem. This trips everyone up. Remember that 13-stage pipeline?
The assembly line, yeah.
When an instruction at, say, address 1000 causes an exception, the program counter, R15, has already moved on. It's been prefetching instructions ahead in the pipeline, so the PC might actually be pointing at address 1008 or 100C already.
It's living in the future.
It's living in the future.
Yeah.
So when the hardware saves the PC to the link register as the return address, it's saving that future address. If you just return directly to that address, you'd skip over a few instructions.
So you have to manually correct it. The programmer has to do subtraction.
The programmer has to do the math. The return instruction for an IRQ is often something like subs PCLR #4. It says, take the saved return address, subtract 4 from it, and then jump to that corrected location.
That feels like something the hardware should just handle for you.
You would think so. But again, that's the RRC philosophy. Adding complex offset calculation logic to the hardware costs transistors and power. It's simpler and more efficient to just make the software developer subtract a number.
Brutal. And that little S on the end of SUBS is important too, isn't it?
It is the magic key. Adding the S tells the CPU not only to perform the subtraction and jump, but also to atomically copy the saved SPSR, saved program status register, back into the main CPSR. It's the instruction that restores your previous mode and flags and sends you back to your regularly scheduled program all in one go.
It puts you back in the Matrix, as if nothing ever happened.
Seamlessly.
Okay, we're at the last section of our deep dive, and it's titled The Dangerous Shortcut. It's about something called DevMem.
The forbidden door. The break glass in case of emergency tool.
The notes describe it as a way for a normal user space program to get direct access to physical memory. But wait, I thought the entire point of the MMU and the operating system was to prevent that at all costs.
It is. But Linux, in its infinite pragmatism, provides a backdoor. DevMem is a special character device, a virtual file that is literally a window onto the entire physical address space of the machine.
So, I can just write a simple C program, or even a Python script running as a normal user, and I can open this file and just start poking at hardware registers.
If you have the right permissions, yes. You use a system call called map to map a chunk of that physical address space into your application's virtual address space. Suddenly you have a pointer, and writing to that pointer is the same as writing directly to the hardware.
And for quick prototyping, I can see how that would be amazing. You don't have to write and compile a whole kernel driver just to blink an LED.
For hacking around on a Raspberry Pi or BeagleBone in your lab, it's a fantastic tool. It lets you explore and learn how the hardware works very rapidly.
But the notes are filled with warnings, risks.
Massive risks. You have bypassed every single safety net provided by the kernel. There is nothing stopping you from writing to the wrong address. You could overwrite the kernel's own internal data structures, you could corrupt the file system, you could change the CPU voltage and physically damage the chip.
There is no undo button if you accidentally turn off the memory controller.
None. And the other huge problem is concurrency. The real kernel driver might be trying to manage a peripheral, and here comes your little script poking at the same registers via DevMem. You are guaranteed to get into a fight, and the result is almost always a system crash or completely unpredictable behavior.
So the takeaway is, it's a powerful tool for learning and debugging in a controlled environment. But you would never, ever ship a production product, especially not a car or a medical device, that relies on this.
Oh, please don't. For anything real, you write a proper kernel driver that can manage resources safely and correctly.
This has been an incredible journey. I mean, we started with this simple, elegant idea of reduced instructions, and we've ended up deep in the weeds of pipeline flushes, memory barriers, and mapping physical memory into user space.
It really peels back the layers of abstraction, doesn't it? That simple swipe you make on your phone screen. Underneath it, there is this furious, silent ballet of the pipeline fetching instructions, the registers acting as a workbench, the MMU performing constant translation, and the interrupt controller juggling dozens of requests a second.
It really does give you newfound respect for that little black rectangle we all carry around.
It's an absolute miracle of engineering, balancing all these competing demands of speed, power consumption, and complexity.
Well, before we wrap up, I want to leave our listeners with that provocative thought from the end of the notes. It challenges us to think differently about our devices. The next time your phone feels sluggish, or an app crashes, or the back of it feels a little too warm, what's actually happening down there in the basement?
You know, is it a cascade of pipeline flushes because of some poorly written, unpredictable code? Is it a cache coherency issue where one core isn't seeing the updates from another?
Is it a deadlock on a memory barrier? Or maybe, just maybe, some badly behaved app is fighting with the kernel through DevMem.
Let's hope it's not that one.
Thanks for taking us on this tour under the hood of the Cortex-A8. It was fascinating.
My pleasure.
We'll see you next time on The Deep Dive.